Thank you very much. So we do have some cut pieces of metal up here that I will pass along as we get to those parts in the presentation. So just so that I pace myself correctly, could you please raise your hand if you've heard me talk about pair plasmas before? Excellent. That means I don't have to spend too much time on that part. How about winding angle optimization? Yes, I know you know winding angle optimization. You wrote the papers about it. All right, and how about, do you know about non-neutral plasmas? Yeah? Cool. Very nice. All right, if I am going too quickly through some of those parts, please stop me and ask me to explain things that I haven't fully explained or haven't adequately explained. I tend to put in a lot of visuals in presentations. So like we have our splash slide here that at the top has electrodes from positron traps. In the middle has our supported dipole trap, also known as our magnet on a stick. And then at the bottom, our levitated dipole and our stellarator. And I will probably not explain all of the pictures. If you would like a picture explained, you're welcome to raise your hand. And encouraged to raise your hand and let me know what you would like to know about. So I guess with the logistics out of the way, I'd like to say thank you very much for giving me the chance to tell you about what we've done so far in terms of optimizing and designing and doing engineering tests for EPOS. So for putting electrons and positrons in an optimized stellarator, which is what the acronym stands for. And this talk is very much on behalf of everyone in the EPOS team, like Paul and Pedro here in the front row, and Jason, who's not here in person, and our summer students and engineer, and the rest of the Apex PAX EPOS group, of which EPOS is a part, as well as the greater Apex collaboration. So thank you very much for the opportunity to tell you about what we're working on and what we're aiming to do. This is the full collaboration. It's an international collaboration that spans all of those topics that were on the splash screen on the front page. But our center of mass is at IPP Garching, although we benefit very much from our colleagues in the theory department up in Greifswald as well. So the project used to be split between Greifswald and Garching, but at this point, pretty much all of the activities have moved to Garching because that's where the positrons are that we will ultimately be putting into our stellarator. And I think it's a good reminder just how large the coils are for IPP's main experiments. So for the tokamak ASDEX upgrade and the stellarator W7X. And if you look online, you can find these pictures from when the experiments were being assembled, and you can see the people for scale compared to the coil sizes. And if you haven't visited, you should absolutely visit. These are wonderful places to visit, but you don't get to see the coils anymore because they're now built inside the experiments and run by very expert and very large teams. And IPP also does materials research and numerical methods and theory for stellarators and tokamaks and astrophysics and a number of other things. And so, again, this is a reminder of how big a magnetic confinement fusion experiment is. Like when we're looking at coils on the screens, sometimes we forget just how big those coils are. And our coils are not that big. But we've found that despite this large difference in size, there are tools and interests and concerns in common between designing a stellarator for a fusion plasma and designing a stellarator for an electron-positron plasma that is much smaller and in a very different parameter regime. So the group in which from which EPOS was born, and in which we're located is the Apex-Pax EPOS group. So the acronyms are somewhat historical and path-dependent, but we also call the whole thing the APEX collaboration. It stands for a Positron-Electron experiment. I explained what the pictures in the splash screen are, and clearly we're at a different scale and plasma regime than fusion experiments. When we have the goal of studying these mass symmetric plasmas, which are this compelling frontier in fundamental plasma science. And we work with tabletop-sized devices, including one going onto high-temperature superconducting coil-based traps, and the second one being the EPOS Stellarator that I'm talking about primarily today. So the research that we do as a whole is that we accumulate positrons in our Penning-Malmberg traps, our non-neutral plasma traps. We have several different variations on these that I won't tell you about. Here's another picture of one of them there. And our sort of grand challenge is that we want to create these uniquely simple, symmetric, quasi-neutral plasmas. So to make electron-positron plasmas where everything is the same mass, because there are interesting predictions about how these will behave, including that they may not be turbulent in certain geometries and parameter regimes. And we want to use our plasmas and our positrons as sensitive probes for understanding fundamental plasma processes. So the transport of our collection of charged particles across our magnetic field lines and our magnetic geometries, and the interplay between kinetic and fluid effects, and regime crossing between when something is well described by one model or well described by another. And on the way, we hope that we can contribute to the advancement of the state-of-the-art science and technologies that we're using for all of this. So contributing back to the fields of non-neutral plasma physics and engineering of HTS coils, and I hope also stellarator design. So this is the graphic of the sort of stuff that our collaboration in our group works on. Again, with some pictures for visual aids. This is what our day-to-day activities look like when they work. And we're sort of located at the intersection of all these things, but we'll be focusing on the magnetic confinement and the pair plasmas, well, 4 pair plasmas for today. So I mentioned that we're in a very different parameter regime, and as a reminder, we've got this very nice diagram for the Contemporary Physics Education Project that shows you your orders of magnitude variation in density and temperature for the sorts of plasmas across the field of plasma physics and across the universe. And most lab astrophysics or basic plasma science plasmas tend to be the orange and red stars, and we're looking at much lower densities, and we're on the low temperature end. And we're very far away from the magnetic fusion reactor at the top. And so one thing that we have to worry about is that we need to make sure we get to have a plasma in the first place, because antimatter is hard to come by. And so we're generating our plasma by collecting antimatter and then combining it with matter. And so we need to get up to the point where we're sure that we have the collective behavior of many charged particles, where we reach densities, high enough densities and low enough temperatures that this competes with the applied electric and magnetic fields, which has its pros and cons, because that can then make your plasma leak out of the device faster than you'd imagined it would. And in terms of we're usually thinking when we're designing our experiments at the individual particle description, although we get into the fluid description a little bit, and especially our colleagues and collaborators in theory help us out with that a great deal. Let's see. So since most people have heard about pair plasmas, as a quick reminder for anyone who didn't raise their hand, because mass asymmetry is a cornerstone of the physics of non-neutral plasmas, it's very interesting to explore what plasma physics would be like if everything were the same mass. Some things don't change very much. You just get like an extra square root of 2 in a dispersion relation or something like that. But other things changed quite a bit. There are many predictions for this, and we would like to generate some experiments to test this. And the idea is that by understanding plasma in this fundamental limit, where you don't have the mass separation and the length scale separation and the time scale separation between the positive and negative species, this will improve our understanding of plasma physics. It's this quintessentially symmetric plasma that we then want to put into symmetric or quasisymmetric configurations. And we also, a lot of the motivation for studying pair plasmas is that they also exist naturally, in addition to being this very interesting basic plasma physics object for theory and simulation. So they occur out there in the universe, and there are a number of astrophysical reasons for looking at pair plasmas. We're not the only ones who want to do this. There are other approaches to studying pair plasmas in the lab. You can make a pure positron plasma and put an electron beam through it. So this was done 30 years ago. You can generate relativistic pairs using either high-powered lasers or proton beams. Or you can make plasmas with negative and positively charged ions, in this case C60. And all of these experiments that have been done so far have been beam experiments. And what we would like to do is to actually trap the two equal mass, opposite charge species in the same volume so that they can interact over as long time scale as possible. So our approach is that we would like to do low temperature electron-positron plasmas in toroidal traps. We would like to get many Debye lengths with both species magnetically confined for as long as possible. And this is the overall scheme that we want to use to do this. So we're using the world's best source of low-temperature positrons, which is named Nepomuk. That's in the red box. Then we accumulate the positrons in a series of non-neutral plasma traps. Those are in the green boxes. Or we will once we put this all together. And then we put them into either of two magnetic confinement devices that are tabletop-sized and based on HTS coils, with the one being a levitated dipole trap and the other being a stellarator. There are other places to get positrons from, but the reactor-based source is the best when the reactor is running, which we hope it will be again next year. And in terms of needing all of the non-neutral plasma traps, we need to get up to the total number of positrons that we need to make a plasma with the velocity distribution function that is suitable for putting them into our traps and then getting our short Debye lengths. For those who didn't raise their hand on the non-neutral plasma part, so non-neutral plasma traps are very effective for trapping a single sign of charge, and this is the standard way to accumulate antimatter. So you take a uniform magnetic field and put in an axial potential well that you create by putting in a stack of hollow cylindrical electrodes, as shown there. And then you can trap a single particle or a whole cloud of particles that behaves like a charged fluid. And the charged particles follow the magnetic field back and forth, but then they're trapped in the potential well that you apply with your voltage. And you can fill it up to either the space charge limit, or if your magnetic field isn't strong enough, the limit where it's spinning around itself so fast that it flies apart. And this type of trap can be used to trap antimatter by itself for days or weeks or months or years. So it works extremely well. There's a picture of one of them there on the bottom that we use to trap positrons. And another thing about non-neutral plasmas is that this is a niche field of plasma physics. In terms of the trapping of electrons, this has been around for many, many decades. It first came out of studying charged particle beams and finding that they had collective effects. And then people wanted to study those collective effects, so they started trapping the charged particle beams in non-neutral plasma traps, and that's how the field evolved. And one of the things that's notable about it is that it's this paragon for precise comparisons between the theory of charged particles in these traps and then the experimental data and the simulation, and it looks at the fluid effects and the kinetic effects and the links between them and the effects of asymmetries. And for this reason, the field of non-neutral plasma physics is, in addition to enabling us to make electron-positron plasmas by collecting the positrons is also an inspiration for wanting to look at these mass symmetric plasmas in these symmetric magnetic fields, or quasi-symmetric. As a side note, though, that asterisk is because these precise comparisons are primarily in linear traps, like the one that's shown there. Non-neutral plasmas have also been made in what for the field are more exotic geometries, like magnetic mirrors or cusps, or purely toroidal fields, or dipoles or stellarators. The toroidal fields, as a side note, work very well for non-neutral plasmas because the plasma rotates around itself due to its space charge, and that gives you a rotational transform. So you can trap a non-neutral plasma in a toroidal field, even though it doesn't work for a quasi-neutral plasma. But from these configurations, the ones that we think are the best bet for neutralizing a quasi-neutral plasma or putting in electrons and positrons, the matter and the antimatter together, are the dipole and the stellarator. So we have these two companion devices for confining the pair plasma, the levitated dipole trap and the stellarator. Obviously, there have been other stellarators out there, and there have also been other levitated dipole traps out there, but we're trying to make them smaller and high-temperature superconducting. And we've achieved that with the levitated dipole trap, and thanks to this collaboration, we're on the way to achieving that with the stellarator as well. So once we're able to combine the electrons and the positrons in the companion traps, we want to study the transition to this regime of collective quasi-neutral behavior, look at its stability with the different geometries, with different density and temperature profiles, with or without temperature symmetry, because when we're building the plasma from the two charge species, there are knobs that we can turn there. The first thing we can study is transport and what limits the confinement time, and then the robustness to different asymmetries. So as I mentioned, the theory of non-neutral plasmas and pair plasmas and toroidal geometries is still very much an area of active research. And Paul Costello, who's here, did his master's thesis looking at pure electron plasmas and stellarator geometries. Patrick Steinbrunner did his PhD thesis looking at pure electron plasmas and dipole geometries. And stellarator theory has done a lot of work looking at pair plasmas and toroidal geometries as well. That's helping to guide and inform, and we will use to compare against the experiments. So the plasmas that we're talking about, again, are tabletop-sized. We would like to have a very large magnetic field. This is, again, inspired by the field of non-neutral plasma physics, because that is a very useful tool in that field for cyclotron cooling. Because unlike fusion plasmas, which you want to be hot, these plasmas, we want them to be cold, not only to get the Debye length smaller, so that we can make sure to have collective behavior, but also because if our positrons get too hot, they will start annihilating on residual neutrals, and if our electrons get too hot, they'll also ionize residual neutrals. And at these densities and temperatures, we expect not to be limited by annihilation, even though we're putting matter and antimatter together in the same volume. There's a lot of information out there in the literature about the cross-sections for annihilation between electrons and positrons through different mechanisms, whether they annihilate without recombining, without forming a bound state first, whether they radiatively recombine, so a photon carries away the additional energy and they form a bound state, or recombine through three-body recombination, so a third particle carries away the energy and as they form a bound state. And so the purple and green and blue lines are all looking at what the lifetime of the pair plasma would be if it were limited by each of those types of loss mechanisms. And they're all extremely long for the range that we're looking at. So really the only thing that we have to worry about is not having residual neutrals and keeping our temperatures cold, because this lowest line down here, that 10 eV there, is a turn-on energy. So if our positrons are cold enough, that won't happen, and then the annihilation times are much longer than we assume our confinement time will be, although we don't exactly know what will limit the confinement time. We're we're working on that. So to summarize, we're aiming to make a symmetric quasi-neutral plasma in what's traditionally the non-neutral plasma regime, and using the tools and being inspired by the physics of non-neutral plasmas. We are well on our way there. So what I show here on this slide is the beam tube for the Nepomuk beam in the heavy water tank of the reactor in Garching, the buffer gas trap system, and the multi-cell trap that we've built in our group so far, the levitated dipole coil, and then the goal here is to fill out that last box on the bottom right. So the concept is to use our common techniques and resources, the electron beams and the accumulation, and that we know how to move the positrons across flux surfaces into closed field lines, and that we have gamma diagnostics and schemes for measuring these plasmas based on the annihilation, and using our knowledge of HTS coils and cryogenics and UHV, and building a stellarator that we can then compare the behavior of the pair plasma in the stellarator and the confinement and the transport to the dipole. Because magnetic geometry, as everyone here knows, is very important to what the behavior of your plasma is going to be. And so this was the old concept when we first started thinking about this a number of years ago. And I did not want to wait any longer to show the new concept, because I wouldn't want anyone to think that we were still using the old concept. So this was the original idea that we would have, just like in our dipole trap. There it is. We would put our high-temperature superconducting coils in our vacuum inside a simply connected chamber, so we don't need to put a chamber inside our coils. We can use a simple vacuum tank and put the coils in that. But we didn't know what the shapes of the coils would be, and so now the stellarator is taking shape, both literally and figuratively. These aren't the final coil designs. But you see several iterations of our coil test program here. So Pedro did a configuration design review at the end of January. Many of you were there and gave feedback that he's been working through, and we'll have an engineering design review within the next couple months. And then we hope to finalize the CAD models and order the parts and put it together within the next year or so. So figuring out what we wanted to build, even though we had all this prior knowledge about working with HTS and injecting positrons and creating electron plasmas and gamma diagnostics, there were a lot of new questions about optimization-related physics engineering interplay. So I've listed some of these here. Can you even make a small stellarator out of HTS coils and have it have good confinement? How many coils do we even need or want to include in the optimization? How precisely do they need to be fabricated and installed? Is that even possible with the materials that we would like to use? And how much quasi-symmetry breaking is expected, necessary, and tolerable while still having sufficient confinement? So Paul, Pedro, Jason, Tristan, people in the group have been tackling in parallel and looking at the interplay between the physics, engineering, and optimization constraints, looking at a device with these parameters. So the question about the HTS coils. So for those who aren't already intimately familiar with winding angle optimization, conference lanyards are a really good tool for looking at this. So when you have a conference lanyard, if you want to wind this into a circular coil, there's the obvious way to do it is that you wind it this way, right? You don't try to wind it this way. And so you want to use the binomial curvature to wind your planar coil. But what if your coil is non-planar? Then you have to worry about binormal curvature and torsion. And so those are illustrated there on the right-hand side. And the structure of the tape is another thing that I've included here. So the HTS tape has two sides. It has essentially a belly and a back. So on one side, you have the substrate that provides the stability for the entire thing.